Okay, so we're starting with our logs. We just came off of a unit on inverses. Right, inverses. So we wrote an inverse like F inverse or G inverse or things like that. And it turns out that the inverse of an exponential function, exponential, the inverse of an exponential is a logarithmic. Okay, that's important to understand when we're graphing these things. So if I were to graph an exponential function, okay, hopefully you remember this from Algebra 2. An exponential function has a horizontal asymptote through the origin, right? We're never going to get to be 0. It usually crosses your x-axis or y-axis at positive 1, and we experience exponential growth in this manner. Okay, so if we consider the exponential equation 2 to the x, right, we can make a table of values. So if we have 2 to the x, here's negative 2. Actually, these are going to be x's, and this will be your 2 to the x. So negative 2, negative 1, 0, 1, 2, right? Those will be fine values. This is 1/4. 2 to the negative 2. Okay, so we'll talk about that property real quick. If we have a negative power, that becomes a positive power when you put it in the denominator. Okay, so that's how we deal with all these exponentials. If they have a negative power, they become fractions. Okay, so this is 1/2, and then of course anything to the 0 is 1. So 2 to the 0 is 1. 2 to the first power is 2. 2 squared is 4. Okay, so we can plot these points on here. Here's the point 1, 2. Here's the point 2, 4. I guess I have to change my graph a little bit to accommodate this. I know there's no room on your notes for this, but that's okay. We're just doing a little exponential versus a logarithmic. Okay, so there is your exponential graph of 2 to the x, right? Pretty basic. Sometimes we call that the parent function for our exponential. Okay, so if we were going to graph its inverse, right, the inverse of it, so here we have, I don't even know what to call it, 2 to the x inverse maybe. We're going to switch your x's and your y's. So here we have 1/4, and then we have 1/2, and then we have 1 and 2 and 4. And then here we have negative 2, negative 1, 0, 1, and 2, right? We switch our x's and our y's, so the x's that were here are now your y values of your inverse. Okay, so this is 2 to the x, not 2 to the negative x, but the inverse of 2 to the x. So if we plot these, 1/4 negative 2, well that's right here, right? 1/2 negative 1. 1, 0 is right here, 2, 1 is here, 3, 4 is here, right? Notice that these graphs look like they are indeed symmetrical across the line y equals x, and that's what it means graphically to be an inverse of each other. They are symmetrical across the line y equals x. So our horizontal asymptote from your exponential becomes a vertical asymptote for your logarithm. Okay, so log will never be negative. You can only take the log of a positive value, right? That's one of our properties of logs. What's the log of negative 2? Right, it doesn't exist. It's not the thing. So a log, in fact, this is log base 2. Okay, so we'll talk about this in a minute, but the base of your exponential is going to be the same as the base of your log when we do the inverse. So a log and an inverse are, a log and an exponential are inverses of each other. So let's notice our inputs. Our inputs are there's 1 up for every input, right? They're increasing by 1. And what's happening to our exponential? Be multiplied by 2. But if we look at our inverse, as your outputs increase by 1, notice now we have our output increasing by 1. So our output is the constant plus 1, plus 1, plus 1, and our input values are being doubled. Okay, so this is always true with an inverse, is that your inputs and your outputs are switched. Okay, so enough background information. Let's jump into doing some of our worksheets here. Okay, inverse operations. Okay, so we can have an exponential or we can have a logarithmic. Okay, an exponential or a log form. So that's what we're going to be doing mostly today, is we're going to be rewriting exponentials as logs and rewriting logs as exponentials. Okay, and it's just a matter of rearranging your furniture. We're going to take our couch and we're going to put it against that wall. We're going to move the coffee table over there to that corner. We're going to put the TV and all of its stuff over here on this wall. Okay, so your exponential form looks like this. We have, I don't know, y equals some base, right? So we'll call the base b. This is your base raised to some exponent, right? So that's your exponential form. This is the base, right? So this is the base of your exponent. This is the exponent of your exponent. And this is the answer for your exponent. Let me change colors in case green isn't very easy to see. This is the answer. Okay, so these are the three parts of your exponential. There's an answer, there's the base of your exponential, and there's, of course, the exponent. So we're going to change this and write it as a logarithm. And of course, what we first need is a log. So you write the word log. Okay, you can't have a logarithmic expression without the word log. Now, the base from your exponent becomes the base of your log. Okay, so that's a little micro, like a subscript. The base is written below the g of the log. Okay, it's important so that everything isn't all jumbled and looking crazy. The base goes down there. Your answer goes here. Right, this is now your answer. I meant to make this a blob, not another box. And your exponent goes here. Okay, so anytime we want to rewrite an exponential as a log, we will rearrange the furniture. The base of your log, the base of your exponent becomes the base of your log. The answer for your exponent becomes the argument for your log, and the exponent becomes the answer for your log. Okay, we're just going to rearrange the furniture. So let's see if we can do that for these next 4 problems. Convert the following equations. Oh, some other things. If you don't see a number, but you do see the word log, that's log base 10. Okay, that's called the common log. Our numbering system in America is a base 10 numbering system. Right? We count 10 units and we get another placeholder. 0 through 9, and then we go 10, 1, 0. And then you count another 10 and you get 2, 0. And then you count another, you get 3, 0, right? So every 10, we get a new digit every time. So we have a base 10 numbering system. Okay, so what's the base of our exponents? The answer is 3. What's the exponent of our exponents? 2. And what's the answer? 9. Okay, so when we write this as a log, we first write the word log. Okay, and then we say, what is the base of our exponential? 3, and that becomes the base of your log. What is the answer for your exponential? 9, and that becomes the argument for your log. And then what is the power of your exponential? 2, and that becomes the answer for your log. Okay, and that's all we have to do. Right? If we're going to rewrite an exponential as a log, you first start by writing the word log. Okay, let's see what else. 10 to the x equals y. Okay, so we start with log. And the base of our exponential is 10, so that goes down there. The argument is, I guess the answer is y, and our exponent is x. Okay? And there's nothing that you have to do with that. You just leave it as it is. Log base 10 of y equals x. All we're doing is we're rewriting it as an exponential or a logarithm. Okay, so in practice, you're not going to see the 10 down there. It's just going to be log of y. Okay, and if you don't see a number as your base, you're going to always assume that it's a 10. Log base 10. Okay, r to the t power equals w as a logarithm is log base r of w equals t. Okay, so this is how we say that. Log base r of w equals t. So you say the word base before you actually say what the base is. Log base r of w equals t. Okay, log base e, so e, so now we've switched the directions, right? The base of your exponential is still the base of your log. And now your answer is y equals our power of 3x. Okay, now we should talk about this because you won't see log base e either. Log base e is better known as natural log. So if we ever have a log base e, right, don't leave it as log base e, change log base e to be the natural log, because e is the natural number. So let's see if we can switch that around. Given a log, can you write it as an exponential? Okay, and of course the answer is yes. Yes, you can. So first we start with the base. The base of our log is 7, so the base of our exponential is 7. Okay, our power is the answer, so that's 7 squared equals x. 7 squared equals x. So yes, 49 could be the answer, but we're going to leave it as an exponential and not evaluate. Okay, our base here is 3. So 3 to the x power equals y. 3 to the x equals y. Okay, we're just rearranging our 3 parts. The base, the exponent, and the answer. I don't see a base. So what is the base? 10. If we don't see a base, you're going to assume that it's a 10. So 10 to the second power equals y. Okay, so we are rearranging our furniture. What about natural log? What is the base for natural log? That's base e. E to the 4th power equals c. Okay, excellent job. So whenever we want to rewrite it, right, these are inverses. The log and an exponential are inverses of each other. Okay, so we're writing an inverse equation every time that we are changing from one form to another. And that's what we're going to do down here when we evaluate these logs. Okay, so each of these have a numerical answer. That's what it means to evaluate. What is the value of? Okay, the answer to an exponential, the answer to a log is an exponent. So when we are evaluating these, we're going to think of it as an exponential. We're going to think of 2 raised to the what power equals 8. Okay, this is what you have to think about in your brain. The answer is the exponent. how many how many 2's do I multiply together to give me 8? And the answer is 3, because 2 to the third power equals 8, and the answer is your exponent. Okay, the answer is always an exponent. So 5 raised to the what power equals 25? And that's 2, because 5 squared equals 25. So the answer is your exponent. The answer is 2. 2 raised to the what power equals 32? How many 2's do I have to multiply together to get 32? And the answer is 5 of them. So my answer is the exponent. 2 to the 5th power equals 32. Okay, what's my base here? 10. So 10 to the what power equals 100? 10 squared, right? So there's lots of ways that we could write a 2, because anytime we're having a power that's being squared, the answer is 2. Okay, maybe there's some tricky ones. Aha, here's a tricky one. 16 to the what power equals 4? Okay, so remember, the answer is an exponent. So what operation do we have to do to 16 in order to change it into a 4? We could take its square roots, right? We can't multiply or divide by a number. We want to do one operation, and that's to square root. If we square root 16, we get 4. So how do we represent the square root as a power? That's to the 1/2 power, because we're looking for the square root. So 16, log base 16 of 4 is 1/2. Sorry, 1/2. Because the square root is the 1/2 power. What if we had the third roots? That would be to the 1/3 power. Okay, whatever the root is becomes the denominator of your fraction. So anytime we're taking a root, that's a fraction as an answer. Okay, 3 to the what power equals 1? And that's 0. Okay, anytime your answer is 1, then the log of that is always going to be 0, no matter what your base is, because anything to the 0 power is 1. Okay? Right, so we're answering, the answers are exponents. 10 to the what power equals 10? And that's to the first power. Okay, because anything to the first power is itself. So this is what we do when we are evaluating. We're asking ourselves, what is the power? 6 raised to the what power is 1/36. Okay, so how we do this is we change our 1/36 to be 1/6 squared, right? We want to have the same bases. If we have the same bases, then the exponents are equal. Okay, so we rewrite 36 as 6 squared. Now, what is our exponential rule about denominators having powers? We can take them out of the denominator by making them into a negative power. Okay, so whenever we have a number turning into a fraction, that's going to be a negative power, so our answer is negative. So just some generalities. Whenever we see this raised and our answer is a fraction, that means we have a negative exponent. Okay? So that's probably how these are used most often, is to evaluate this without a calculator, because the answer to an exponential is, the answer to a log is an exponent.